In general chemistry, we learn that we have to have a few things for a reaction to occur. We need things to hit, we need them to hit hard, and we need them to hit where it counts. In organic chemistry, we think a lot about how these collisions form and break bonds by moving electrons to specific locations. We used curved arrow notation to show this movement, which we have already started to use when we talked about resonance structures. Drawing curved arrows is a really important tool that we use to describe the mechanisms of reactions. Learning to do these well will make the difference between memorizing every single reaction that could occur and recognizing patterns of reactivity. The latter is easier in the long term and infinitely more valuable. Curved arrows are always used to represent the movements of electrons to form a new bond, not ever the movements of an atom. For most of our reactions, we'll use arrows that have barbs on both sides, as I've shown here. These arrows represent the movement of two electrons from the back end of the arrow to the location that the arrow points to. Late in second semester, we will use arrows that only have one barb indicating the movement of a single electron. That's a little bit radical for right now, so we'll focus on the normal double-barbed arrow. If we want to show bond breaking, we draw an arrow from the bond to the location of the electrons in that bond will eventually reside, usually an atom, sometimes a double or triple bond that pushes electrons around elsewhere in the molecule. You can see this with the HCl bond being broken below. To show a bond forming, the tail of the atom goes on as a source of electrons, like a lone pair or a double bond, and to the atom that will now be bound. You can see this with the new bond from oxygen to the hydrogen in the product shown. Notice that these steps happen at once as shown. We can't exceed the standard valence, here too, for the hydrogen, so we have to have one bond broken as the other is formed. One of our most common reactions, especially in enzyme mechanisms, is the proton transfer reaction, the standard Bronsted-Lowry acid-base reaction. Remember that in the Bronsted-Lowry definition of acids and bases, an acid is something that can donate H+, which are just protons, and a base is something that can receive them. A proton transfer step, mechanistically, is just a bond being broken between the acid and its proton, while it's being formed between a base and that same proton. Let's think about how we draw that notation. Try to draw the arrows as we describe them and check your work at the end. If we look at the acid-base reaction between NH3, ammonia, and water, we can see that a hydrogen from water is being taken away by nitrogen. For that to happen, the lone pair electrons on nitrogen need to form a new bond to hydrogen, which we draw with an arrow from nitrogen's lone pair going to the water's hydrogen. So an arrow going from the nitrogen lone pair to the water's hydrogen. The other thing that needs to happen is that the water, the acid in this reaction, needs to give up the hydrogen. That bond needs not to be there. So the electrons from the OH bond are pulled back to the oxygen, indicated by an arrow from the OH bond going to the oxygen. It should look like this. Since we are starting to talk about reactions and acids and bases, we should remind ourselves that we generally think about reactions being possible in both directions and being governed by equilibrium. The equilibrium should always have the same balance under standard conditions. So we can talk about an equilibrium constant that describes a reaction's tendency towards forming product. We do this by taking every concentration or partial pressure of products formed in a reaction raised to the power of their coefficients, and then we divide that by the concentrations of the reactants raised to their powers. A generalized form of this statement is shown. Because the KEQ values are defined products over reactants, very high KEQ values indicate the more product being formed, and very low KEQ values, think close to 0 rather than negative, indicate more reactants in the denominator. This type of equation can be written for a generalized Bronsted-Lowry acid-base reaction as well. The acid, HA, and the base, B-, are the reactants, and they form products, A- and HB. Since these reactions are generally described with one proton moving at a time, all the coefficients, and therefore the powers, are 1. Having a generalized acid equilibrium equation is great, because it allows for us to talk about how readily acids will give up their protons by comparing their equilibrium constants. The only problem is we also get variation if we change the base. So instead, we generalize this equation even more, and we talk about water as the base that we use for all of these reactions. The reaction then has B- replaced with H2O and HB replaced with H3O plus, or hydronium. But the water is the solvent, and it won't be considered as part of the equilibrium constant, since its concentration is not going to change. So we can actually simplify this further and talk about just an acid, HA, dissociated into A- and H+. Remember that H+ can be used interchangeably with H3O+ in water. It's hydronium. This is called the acid dissociation equation, and the equilibrium constant for this equation is the same as any other equilibrium constant, products over reactants. We just give it a special name, the acid dissociation constant, which we abbreviate Ka. The Ka is a very powerful tool because it allows us to compare the strengths of acids to each other on a universal scale. I just pulled up a section of a larger list of pKa's on page 301 of your texts. I wanted you to see that even though Ka's are an essential tool, those numbers actually vary over 60 orders of magnitude. This can make the numbers difficult to work with and really difficult to compare. To make things easier, we define a pKa, that is the power of Ka, similar to the pH, the power of hydrogen. So the pKa is just the negative log of Ka, just like pH is the negative log of the H+ concentration. Notice that now we get numbers that are relatively short, easy to compare, and easier to work with. The strongest acids have large Ka values, but negative pKa values. So the larger the Ka, the lower the pKa. The weakest acids have low, that is close to 0 Ka values, but end up having very high pKa values. Most of the reactions that we are interested in aren't straight acid dissociations in water, but are transfers of protons from one molecule or ion to another. That's okay because the pKa still tell us the relative strength, and therefore the direction the reaction will proceed, and we can even use it to determine the KEQ for the reaction. A lower pKa always means a stronger acid, so if a reaction is drawn out, the acids on both sides of the equation can be compared. In this example, acetic acid, which is shown on the left, has a pKa of 4.75, while methyl ammonium, which is on the right, has a pKa of 10.63. Since 4.75 is lower, acetic acid is a stronger acid, and the reaction will proceed to the right. The power of the equilibrium constant, that's the pKeq, for the reaction, will simply be the pKa of the reactant acid minus the pKa of the product acid. In this example, the PEQ should equal negative 5.88. We can see that 10 to the negative power of the PEQ gives us KEQ, which ends up being 7.6 times 10 to the 5th, as shown. So again, comparing the pKa values not only tells us the direction of the reaction, but also allows us to find an equilibrium constant for the reaction indirectly. It is, however, important to remember that acid-base reactions, like all other reactions, still require a collision. In a solution, this collision is far more likely to happen with a solvent than with any other molecule. If the solvent can function as a base, it will do that and then functions as an acid to the other molecules. This has the important implication that the actual acid present in aqueous reactions is actually hydronium, the H3O+, not HCl or any other strong acid. And the actual base in any of these reactions is hydroxide. It can't be anything stronger than hydroxide. So sulfuric acid and hydrochloric acid might have different pKa values, but it doesn't matter when they're in water, since hydronium will be the H+ donor that actually matters and meets something else in solution. Another implication of equilibrium is that changes to a system at equilibrium will result in an adjustment to compensate for that change, Le Chatelier's principle. For example, if we are at equilibrium with these tanks and we add the product H+, the extra H+ will force more of the product A- to react and form HA. I'm going to say the same thing in two different ways. Adding product shifts the reaction towards the reactant. Adding acid or dropping pH results in more molecules being protonated. Conversely, if we increase the pH, the same as decreasing the concentration of H+, we will have every acid protonated less of the time. Percent dissociation gives a quantitative way to look at this. When we're close to the equilibrium, we will have any increase in pH drastically increase the amount of acid that is deprotonated, and decreases in pH will result in much lower amounts of dissociation. Interestingly, the point when half of the acid is HA, protonated, and half is A-, or deprotonated, is the pKa. Also worth noting is that by the time you are 1 pH unit above the pKa, practically all of the acid is in the form A-, and by the time you are 1 pH unit below pKa, practically all of the acid is in the form HA. This actually all springs from the maths. Let's walk through these maths together. First, let's agree that acids can be dissociated, and they are governed by the acid dissociation equilibrium constant as shown. Let's arbitrarily take the negative log of both sides. Done. That looks interesting. Let's also separate out that negative log H plus from the other part of the negative log on the right side. Remember that when something is multiplied inside of a log, it can be commuted out as an added log of that item, as we can see here. These steps may seem arbitrary, but notice that we have just related two definitions in our equation. The negative log of Ka is defined as pKa, and the negative log of H plus is defined as pH. This equation now allows us to easily compare pKa and pH to determine the ratio of deprotonated to protonated acid. Yeehaw! This equation is known as the Henderson-Hasselbalch equation, and it is one of the most important equations in chemistry. You should absolutely either memorize this equation or be able to derive it from the Ka, just like we did. I always have trouble remembering which thing goes on which side and what signs things have, so I derive it every time. For some of you, the value might be more apparent if we modify this even a little bit more. Let's move the pH and the pKa to the same side and minimize the negatives, like so. Finally, we raise the 10 to the power on each side. On the left, it gives us 10 to the pH minus pKa, and on the right, it gets rid of that log. For most people, it's easier to see the value here. If pH is greater than pKa, we know that 10 will be raised to a positive power, and we'll have more A- than HA. If pKa is greater than pH, we know that 10 will be raised to a negative power, and that will give us more HA than A-. And if pKa and pH are equal, we will raise 10 to the 0 power, which equals 1, meaning A- and HA are equal. These conditions are the same ones we mentioned in the last slide, but now we have a way to quantify this relationship. Let's try a practical example of this. This is my favorite amino acid, valine, which goes by the three-letter code VAL. It might be helpful to know whether this biological molecule will be charged or uncharged in the bloodstream, which typically has a pH of around 7.4. We can look at each acidic group and gauge what form it will take using this rearranged Henderson-Hasselbalch equation. Let's first look at the carboxylic acid with a pK of 2.29. Since 7.4 is greater than 2.29, the power of 10 will be positive, and we will drastically favor A-, the deprotonated version, over HA. On the other hand, the pKa of the ammonium group is larger than the pH. That will give us a negative power of 10, indicating the protonated form will be dominant. So this molecule will actually have both negative on the deprotonated O and positive on the protonated N charges as it occurs in the bloodstream. In case you haven't already noticed, acid and base reactions are really serving as a stand-in for us to talk about a lot of the considerations that we give to reactions in general. Another important way of thinking about whether reactions, acid, base, or otherwise, will proceed is the change in Gibbs free energy, indicated as the delta G of reaction. We generally are going to assume for this delta G of reaction standard reaction conditions, like 298 Kelvin, 1 atmosphere of pressure, all concentrations being 1 molar in water, and indicate all this by saying delta G naught of reaction. That naught is the degree sign or 0 that you see. In Gen Chem 2, you learned that the delta G naught of reaction is related to the KEQ by the following equation. In this equation, we know that R is both constant and positive. T is variable, but by definition positive, since temperature in equations is always Kelvin, and Kelvin can't be negative. We also can determine the sign of the natural log of KEQ part of this, based on whether the KEQ is above or below 1. The natural log of KEQ is positive when KEQ is greater than 1. Remember that this corresponds to a product-favored reaction. Since we know all the signs in this case, when KEQ is greater than 1, you have a negative sign multiplied by a positive R, T, and a positive natural log of KEQ, meaning that you'd have a negative delta G naught of reaction. So, whenever product is favored in a reaction, delta G should be negative. We call this exergonic, which is the free energy version of enthalpy's exothermic. Another way of saying this is that reactions are going to go to products when free energy is released. On the other hand, when KEQ is less than 1, that makes the natural log negative. This makes delta G naught positive, which we call endergonic. Endergonic reactions favor reactants. We can also use pKa to predict the direction of the reaction too. pKa is already a negative log, so it can be substituted in for the natural log of KEQ, but we're always going to have the opposite sign. So when the pKa is negative, so is the delta G naught. The only acids that will favor complete deprotonation are those that have a negative pKa. Every other acid will have only partial deprotonation in pure water. The delta G naught of a reaction isn't just related to KEQ. It is also related to the change in enthalpy of a reaction. That's the change in heat energy, as indicated as a delta H naught of reaction, and also related to the change in entropy, indicated as a delta S naught of reaction. Entropy tends to change most when there is a change in number of products or change in state relative to the reactants. This doesn't happen in acid-base reactions often, or organic chemistry that often for that matter. If delta S contributes little in the types of reactions, we can generally say that the change in enthalpy is a good approximation for the change in free energy. This is helpful because it is easy to measure heat, but it's hard to measure free energy. We use different terms to describe the change in heat than free energy. A positive delta G is endergonic, whereas a positive delta H, which indicates heat being absorbed, is endothermic. Likewise, a negative delta G is exergonic, while a negative delta H is exothermic. Again, in organic reactions, an exothermic reaction often is also one that favors products. We'll often use delta H to give hints that delta G probably is the same sign, but we'll talk about delta G for the development of theory. So delta H is usually a good approximation, but we'll talk about delta G because that's the one that's always technically correct. One of the most important aids in our understanding of reactions and their mechanisms is the reaction free energy diagram, where Gibbs free energy, the delta G, is plotted as a function of the reaction coordinate. A reaction coordinate is a variable that corresponds to the changes in geometry on a molecular level as reactants are converted to products. The simplest information we can get from a reaction coordinate diagram is the relative free energy of products and reactants. You can see that as the delta G of reaction. The reaction on the left is an exergonic reaction, and the reaction on the right is endergonic. But we can learn a lot more by learning to understand these diagrams well. For any reaction to occur, we must proceed through a transition state that is higher in energy. The energy it takes to get from the reactants to the transition state is the delta G naught double dagger, or the free energy of activation. We'll just call it activation energy. Any individual particles reacting must have at least this energy in order to react. We can also notice that the transition states for exergonic reactions are located closer to the reactants, further on the left, meaning they look more like the reactants. Try to identify what does the transition state for the endergonic reaction look most like, products or reactants. We will use and create these diagrams frequently in this class. We can fairly easily give an estimate of the pKa of any proton based on the functional group of which it is part. Even though the skeleton might change, the acidity still tends to be fairly consistent. So you can see in the examples on the right, we have ethanol and isopropyl alcohol both are alcohols and have similar pKa's. Similarly, the acetic acid and the benzoic acid both have similar pKa's and are both carboxylic acids. There are, however, a few things that can change the acidity of a proton, the first of many being nearby electronegative atoms that can drastically decrease the pKa, making the proton more acidic. This is called the inductive effect, and we will talk about it in more detail later in this lecture. Note the difference between trichloroacetic acid and acetic acid pKa's. Resonance structures that could stabilize the conjugate base will also drastically increase acidity, as you can see by comparing the ethanol and phenol pKa values. The phenol has a much lower pKa because we could have resonance structures with the aromatic double bonds. We can also think about pKa based on the overall energetics of a reaction. We know that the more endergonic, the higher the pKa and the less acidic the proton. We can judge the extent to which a reaction might occur and its direction by looking at relative stability of products and reactants. Recall from talking about resonance structures that there are two major factors that affect stability more than most others: complete octets and minimized formal charges. A proton attached to a positively charged atom will always be less stable and therefore a better acid. A straightforward example of this is the autoionization of water. We know that since the products are charged, they will be higher energy than the reactants, which mean the reaction is endergonic and will favor the reactants. Here is another example. We can see that ammonium, NH4 positive, is already a little bit less stable, and only one charge is going to result when it reacts with water. We can see this in the blue diagram. This reaction is endergonic, but only slightly. There will only be a slight favoring of ammonium over ammonia in this reaction. On the other hand, NH3 ammonia is on charge, and so if it begins as the reactant, it's more stable than ammonium. When it reacts as an acid, it becomes negatively charged, and the water becomes positively charged. This reaction, shown in red, is very endergonic and will greatly favor the ammonia over the NH2-. The farther to the right an atom appears in the periodic table, the more acidic the protons that are attached to it. Negative charge generated by the loss of H+ is better stabilized on an electronegative atom. You can see this on the two diagrams shown because the NH2- is going to be more stable than the CH3-. How would the autoionization of water compare to the reaction coordinates shown? Bring your answer for this to class. We can also see how stability changes within a periodic table. As we move down, negative charge is easier to stabilize. So having a negative charge on chloride is lower energy than fluoride, but bromine is lower energy still. This is because the larger atoms can spread out negative charge more, which reduces the charge in any individual place. Hybridization also changes the acidity of attached protons. Remember that sp3 orbitals are 25% s, sp2 orbitals are 33% s, and sp orbitals are 50% s. The higher the s character in an orbital, the more functionally electronegative that the orbital is. Since electronegative atoms stabilize negative charge better, the sp hybridized alkyne carbons have drastically more acidic protons. So the more s character, the more electronegative, the more stable the charge, and the more acidic the attached protons. Like 25 orders of magnitude more acidic. A pKa of 25 is still pretty high. It's still going to take a really strong base to deprotonate an alkyne, but it's possible. Delocalization plays an enormous role in the stability of charge. Since charge is unstable, delocalization spreads this out so that no one location has to hold a full negative charge. The difference in acidity between the resonance stabilized ethanoic acid and the unstabilized ethanol is over 10 orders of magnitude. So the more delocalized, the more stability. Sulfuric acid, which can stabilize negative charge over 3 atoms when it loses a proton, has a pKa of -9 compared to ethanoic acid's pKa of 4.75 and ethanol's pKa of 16. We talked very briefly about the inductive effect before, And we know that an electronegative atom near an acidic proton will cause it to be more acidic. But this makes a lot more sense when we think about how the negative charge is better stabilized by a nearby electronegative atom. Anything bound to an electronegative atom will have less electron density from that bond, and then will draw more electrons towards itself in all its bonds, and then will draw more from the next thing's bonds, and so on. So an atom that was holding the negative charge now has less electron density, and so the charge can be stabilized through the inductive effect. The change in pKa's for acids help us to see the effects of electronegative atoms on the stability of anions. But to apply the stabilization of charge in general, we need to generalize for anions and cations. First, most atoms are more electronegative than hydrogen, so we can say that they will generally remove electrons. We say that they are electron withdrawing. Like we saw for acids specifically, electron withdrawing groups will stabilize anions. However, they'll have the opposite effect on cations. There are few groups that are functionally able to donate electrons compared to hydrogen, like silicon or alkyl groups, so like carbon chains, which have the opposite effect. They destabilize anions, but stabilize cations. Like we just mentioned, alkyl groups can stabilize cations because they are electron donating. For this reason, carbocations have stability that is dependent on their substitution. Methyl carbocations are very unstable, but as substitution increases, stability also increases. So a tertiary carbocation is much more stable than a secondary carbocation, which is more stable than a primary carbocation. We just talked about a lot of different factors that affect charge stability, so let's talk about their relative importance. First, if a charge is different on the same atom, the charge species is usually less stable. If the species are charged, we look first to what type of atom the charge ends up on. Charges are stabilized by resonance, so remember to consider that the charge might not actually be primarily on just one atom. And finally, inductive effects can help stabilize or destabilize charge, so look at these factors, especially if all the others are equal. Practically, this method of analysis should allow us to compare the stability of reactants and products in a reaction to assess which is favored. Pause and take a moment to try to compare the reactant stability to the product stability for each of these reactions. And then let's try to work through them all one by one. The top reaction should favor the uncharged reactant, as should the second and fourth. However, the third reaction has a charged reactant and favors the product. We can also rank the acidity of each of the reactants with a similar analysis. The most acidic is obviously the third reactant, since it is the only one that will deprotonate to a more stable product. After this, we compare the charges of the conjugate bases. Those are the things that are on the right. All the charges occur on oxygen, so we next look for resonance. Only the bottom conjugate base has any resonance structures, so that's the second most acidic. Finally, we look at the inductive effect. The closer to fluorine the fluorine is to oxygen, the more it can draw electrons away and destabilize it. So the next most stable conjugate base is the second from the top, and the least stable is the top, meaning the second reaction from the top is going to be the third most acidic, and the top reaction is going to be the least acidic. We can actually line these up to make a generalized reaction coordinate diagram, which allows us to see these acid strengths in a relative sense. So the strongest acid is the one that's the most exergonic, or the least endergonic, which is clearly C, but the weakest acid is going to be the one that's the most endergonic, the one that has the largest increase in free energy caught up in the molecule, and that's going to be A. Base strength of the products can be ranked in this way too. It's just the opposite of the acid strength of the conjugate acids. So the weakest base is the one that went with the strongest acid, and vice versa. We've been talking a lot about charge stability, so let's swing back to talk about contributions to the resonance hybrid, which we've talked about before. Remember, the resonance hybrid looks most like the lowest energy structure, but now we can look at stability with the factors that we just talked about as a third factor for identifying stable structures. For example, we can see that the molecule on the right will have a greater stability or greater contribution to this resonance hybrid because oxygen is better able to stabilize the negative charge than carbon. Or in this structure, the molecule on the right is a more significant contributor because the carbocation is stabilized by an electron donating methyl group. By looking at the charge stability more globally, we can help explain many of our reactivities, acid-base or otherwise. Acid-base reactivities give us a simple stepping point to a wide range of reactions with different mechanisms, because now we can talk about the stability of molecules and ions much better.